Hello everyone, welcome again to Biofluid Mechanics, and today we're going to continue our discussions on the implementation of valves and cardiovascular circuits, for which we use an electrical analogy element called the diode. So what we're going to do today is, if you remember from last lecture, when we try to run the code for the simple circuit with a single valve, there were some issues. Especially during the transition between one state to the other, from the state of the valve being open to the valve being closed, that induced some instabilities in the circuit, or instabilities in the solution process itself, on the numerical solution approximation. And for that purpose, we had to increase the number of time steps and hence reduce the size of the time step size to be able to properly capture the solution. Otherwise, we ended up with a diverged solutions, so a meaningless one. Well, it turns out that we not always can afford to actually reduce the size of the time step to a point where we can actually get a solution, because, as I mentioned before, this particular numerical scheme, or this algorithm, may be actually coded within a feedback control loop on the real-time control of a device in the cardiovascular system, like a pacemaker or a pump. So we actually have to find a way to be as efficient as possible without actually losing accuracy. That is, we have to be able to control the system, the numerical solution process, so as to find an optimal number of time steps in which we can actually resolve the solution. That is not too high for the solution not to be delayed too much. It might not sound like too much, for example, when we say that if we use 10,000 time steps, the solution might take 3 seconds. But 3 seconds might be too long to wait, because remember that one heart cycle lasts only 1 second, and we need to sometimes, certain control systems, like in the left ventricular assist device, need to respond within one heart cycle, so we cannot afford to wait that long. So the idea is that we can come up with a way that we can numerically predict what the order of magnitude of the error will be if we use a certain time step. And if that error is too much and it would actually make the solution diverge, we can on the fly reduce the size of the time step. And then under certain circumstances, we might not need that small of a time step, so we can inflate it back to the original size. That is called adaptive time stepping. So the idea is just to start with a large value time step, like 0.1 seconds, like we tried before and we didn't get an answer. Try to run it, and as we see that the solution might actually start diverging, we actually shrink the size of the time step for that particular set of for the next few time steps, or for the next time values, and then run it that way until we know we can inflate it again. That's in essence, or in summary, how this adaptive time stepping process actually works. So let's come up with a framework behind this, and then I'll show you how to implement it on the code. All right, so let me go back to my doccam. So this is Biofluid Mechanics. And this will be lecture number 20. All right. Now, because of the nonlinearities introduced in the state system of equations by the valves, or diodes, in the case of the electrical circuit. So we know that when we introduce a diode in the system, that leads to semi-nonlinear equations. So this is a removable nonlinearity that we attempted to remove by separating the system into different states, like the open state and the closed state. But nonetheless, after doing this, we notice that in the transition from one state to the next, there are these instabilities. So it becomes a premium to be able to control the time stepping it's an extra P, so as to accelerate the solution process when possible, to maintain efficiency while preserving accuracy and stability of the solution method. Okay, so we notice that when we use too large of a time step, the solution will blow up. So essentially, as soon as a large error is produced by the numerical implementation, that error will propagate and amplify towards the next set of time steps until we actually find something that is completely meaningless. So what we're going to do is use a technique known as Richardson's extrapolation. Can be employed as a way to perform what we call adaptive time stepping for error control. Okay, so how does this work? Well, the word adaptive means that we are going to adapt the time step, and we're going to adapt it such that we keep the numerical approximation within a tolerance, within an error or predefined threshold. Now, how are we going to be able to do this if we actually don't know what the analytical solution, the exact solution? So how can we compute the error? Well, there's a few ways of knowing what the order of magnitude of the error is, or the bound of the error is, not the error itself, because if you know the error, essentially you know what the exact solution is, and this is not possible. But we can know by different ways what is the expected bound of the error, where the error will be within certain limits. We can know what the order of magnitude of the expected error would be. So let's say, for example, we know that the Runge-Kutta time integrator is order delta t to the fourth accurate. That means that if you shrink the size of delta t by 2, you should expect the error to go down by a factor of 2 to the 4. So that's by a power of 16, by a factor of 16. So if you change the delta t by a factor of 10, you should expect the error to go down by a factor of 10,000, right? So maybe we can use this idea to say, for example, well, let's solve the problem, and instead of solving it all the way to the final time, let's solve it only to the next time step by taking one time step, the predefined time step. So you say, okay, I want my time step to be 0.1 seconds. I know it's not going to work, but I'm going to make it 0.1, so the largest possible that I can think of. Okay, and I know that it's going to produce instabilities, but let's see what I can do with it. So I implement the time step of 0.1 second, and then I go back in time, 0.1 seconds, and then solve again by using 2 time steps of half of that. So I'm going to take 2 half steps to the solution after 0.1 seconds, and then compare the two. So the 2 solutions that I got, the 2 numerical approximations, should be at the same time. So it should be at the same time value after 0.1 seconds of the previous time. Then I compare the two. I know that the solution of taking the approximation that I got by taking 2 steps, 2 half steps instead of 1 full step, should be more accurate by a factor of 16 if I use Runge-Kutta, for example. So then I know, if I compare the two, I know what the error or the error bound in the approximation or the order of magnitude of the expected error would be. And then I can use that by defining a tolerance. I say, I want my tolerance to be this much. I don't want my error to be more than this. And if I do get an error in that particular comparison, if I do get an error that is larger than this one, then I'm going to go back and break up the time step into more sub-steps. So first of all, what I do is using a full time step, delta t, get an approximation to the next time level. And 2, using 2 half time steps, delta t over 2. So I get a solution at the next time level using a full delta t, and I get the solution at the next time level, the 2 at the same time level, using 2 half time steps. Okay, then compare the 2. So the first solution would be y at n plus 1 at the first time level should be y at n. So y at the next time level should be y at the previous time level by approximation number 1 plus 1/6 of k1 using approximation number 1 plus 2k2 using approximation number 1 plus 2k3 using approximation number 1 plus k4 using approximation number 1. What I mean by approximation number 1 is this approximation, a full time step. And the 2, the second way would be, well, what if I want to find out what the solution is using the second approximation after half time step, k1, approximation number 2, 2k2, approximation number 2, plus 2k3, approximation number 2, plus k4, approximation number 2, and then figure out what the solution is at the next time level so that I can compare apples to apples. I'm going to compare this one to this one by using this solution at half time step and adding again the new values of k1, k2, k3, and k4 for method number 2. So now I have 2 solutions at the same time value, at the next time step. One by taking a full time step, one by taking 2 half time steps. So then I'm going to apply the theory. And the theory says that this solution, solution 2, this one right here, should be 16 times better than this one. Okay, so then the error bound, so the error bound or the order of magnitude of the expected error between the 2 approximations is error is equal to 2 to the n divided by 2 to the n minus 1 y n plus 1 using the second approximation, y n plus 1 using the first approximation. So notice I'm comparing 2 approximations of the solution at the same time level, okay? But 2 that I got by taking different routes, okay? Where the n is the order of the approximation. And in this case, I use a Runge-Kutta method to get me to the next, to get me to the approximation. So in the case of Runge-Kutta, n is equal to 4. The Runge-Kutta method is order delta t to the 4th accurate. So if that's the case, then for Runge-Kutta implementation, the error for Runge-Kutta will be equal to 16/15 of yn plus 1 minus yn plus 1 method 1. Okay, and we're going to stick with Runge-Kutta from now on. So this is going to be the formula that we're going to use to predict what the error is between the 2 approximations. So the next step is essentially, well, let's use this information. We can use these formulation in reverse to estimate the necessary time step size. We're going to call that delta T max. What is the maximum size of delta T that we need to achieve a prescribed tolerance epsilon of the solution error? So now we're going to use this equation to actually try to find a way to predict what is the maximum delta T that we can afford to use. So delta T max will be equal to delta T, again using this formula or the same formulation, 2n minus 1 to 2n, so I'm using the inverse of these, times epsilon yn plus 1 approximation 2, yn plus 1 approximation 1 to the power of 1 divided by n plus 1. Right? So again, for Runge-Kutta, n is equal to 4, and therefore delta T max for Runge-Kutta will be equal to delta T times 15/16 of the tolerance divided by approximation 2 minus approximation 1, all of these to the power of 1/5. Or you can identify that 16/15 of the difference between the two approximations is equal to the Runge-Kutta error. So basically, the delta T max for Runge-Kutta is equal to delta T, the delta T that you use in evaluating these approximations, the tolerance divided by the Runge-Kutta error to the power of 1/5. And this is a very powerful relationship, because with these, we can simply calculate this and say, all right, we compute this, we compute the two approximations, calculate that error, then put it into this equation with a prescribed tolerance. We say, well, for example, I don't want the error to be more than 10 to the minus 3, so my tolerance is 10 to the minus 3. I put it into this equation, and then I find a delta T max. If my delta T max is larger than the delta T that I use, I'm in trouble, because I use too large of a delta T. If the delta T max that I find, is smaller than delta T, the delta T that I use is too large, so I need to reduce it, I need to shrink it. By how much? Well, by the ratio of these two. I need to reduce the size of delta T. I can only afford my delta T to be as big as this one right here. So this is gonna, after I calculate this, then I can go back and say, well, did I use a delta T that is equal or smaller than this one? So, well, if the answer is yes, it's fine. If the answer is no, then I have to recompute my solution for the next time level using this new delta T. So that's how you adapt the time step. All right. So therefore, an initial course time step delta T can be set up. Okay, so we can start with a large delta T along with a prescribed tolerance epsilon to determine at every time step level, or every time level, if adaptation is necessary. Okay, so I can go one step at a time, literally, and then figure out, based on this formula, whether I need to perform adaptation for that time step or for that time value. And then I do it again in the next time value. If I don't need to, I can actually live with the large time step that I set up. If not, I need to shrink it temporarily until the next time value. That is, if delta T max is larger than delta T, tolerance is satisfied. No adaptation is required. So that means that I already use a delta T that is small enough. Okay, I use a delta T that is smaller than the maximum delta T to achieve the tolerance. So basically, if this is the case, use the approximation error to advance in time as, so the next value, yn plus 1, is equal to yn plus 1, so the first approximation, plus the Runge-Kutta error. This will provide me with the best possible solution for the next time value. So remember, I calculated two approximations on the next time value. Yn plus 1, 1, method number 1, 1 full time step, and yn plus 1, 2, 2 half time steps. So a combination of the two, is given by this formula, will be the best approximation for the next time value. The other choice is, if delta T max is less than delta T, then tolerance is not satisfied. Is not satisfied. So now adaptation is required. So what we do is we subdivide the current time step into NS sublevels. So we need to break up the time step into multiple sublevels. So that is, NS is equal to delta T divided by delta T max plus 1. Okay, and so basically you use the integer of this division, right? So you truncate this. This is a division, a ratio, and you add 1 to it. So this is the number of subdivisions that you're going to need to perform. It's how much the delta T that you originally impose is larger than the maximum delta T that you need to impose, plus 1. Okay, after you calculate these number of subdivisions, then where each time step is now, so the new time step, the subdivided time step, is equal to delta T divided by NS. And what you'll do is perform this validation at every time step. So I'm going to write it here, perform this validation at every time step. So every time you advance in time, you need to do this check and decide whether you need to subdivide or not. All right, so what we're going to do is take this information, this formulation, and this framework, and implement it to begin with on the simple circuit that we worked on last lecture that has a single valve. So implement these methodology in the following cardiovascular circuit. So we had a delta P of the pump, minus plus. This was P0. There was a valve here we call V. There is a corresponding resistance to that valve that we call PV. There's a node P1 where we have C1 and Q1. There's an R, there's an L, there's a P2 with another compliance absorbing or releasing Q2, and then it closes down back into the pump. So basically this is QP, the same Q that goes through the pump. This we're going to call Q, and whatever comes out here is also QP because there's no more diversions. All right, this is the same exact circuit that we analyzed last lecture that ended up having two switch states for when the valve is open and when the valve is closed. So we have two switched states or switched states system. So where the vector is P1, P2, and Q of T. So we're going to write it in that order, slightly different of how we wrote it in the notes last time. So the vector of state variables is this P1, P2, and Q. And if that's the case, the coefficient matrix open for the open state is equal to, let's write it here, minus 1 over RV C1, 1 over RV C1, minus 1 over C1, 1 over RV C2, minus 1 over RV C2, 1 over C2, 1 over L, minus 1 over L, minus R over L. And B0, the right hand side vector, is delta P of the pump over RVC1 minus delta P of the pump over RVC2 and 0. So that's exactly the same of what we wrote, what we derived last lecture, but we just switch columns 2 and 3 and rows 2 and 3 to account for the fact that this is the order in which the state variables are written out, P1, P2, and Q. And the notes for last lecture, we wrote them as P1, Q, and P2. So the equations are the same, it's just slightly with different order. All right, so if the system is closed, or if the valve is closed, then the equations will become a lot simpler. Minus 1 over C1, 0, 0, 1 over C2, and then 1 over L minus 1 over L minus R over L. And the right-hand side vector, when the valve is closed, is actually null, because nothing actually sees the pump. All right, so again, we're going to let the initial condition be equal to P1 at 0, P2 at 0, and Q at 0 be equal to 0, 0, 0. So we're going to let all the solutions start from 0, P1, P2, and Q. And we're going to let R be equal to 10 millimeters of mercury over milliliter second, L 0.1 millimeters of mercury, milliliters second square, and C1, which is equal to C2, equals to 1 milliliter per millimeter of mercury. Also, we're going to let RV be equals to 2 millimeters of mercury milliliter second, so the resistance induced by the valve, and the trigger pressure for the valve is 0. So all you need is a positive pressure differential across the valve to be able to open it. There's no additional threshold. So what we're going to do is implement all these in Lecture 20 MathCAD file. And Lecture 20 MathCAD file is going to be very similar to the one in Lecture 19, except that the code is going to be a lot longer because it's going to contain these checks that we do a solution in 1 time step, a solution in 2 half-time steps, compare the two. If the error that we find satisfies the tolerance, that's the answer. If it doesn't satisfy the tolerance, then we break up time into sublevels and then solve the problem again for the next time level, and then advance in time. All right, so let me go to MathCAD and explain all this. So here's the lecture number 20. Again, we start with origin equal 1. As we have been doing for the last few lectures, to account for arrays starting at position number 1 instead of position 0. Let's assume that the pump has the same form as before. It's a sinusoidal wave in an offset or shift. So we have an amplitude of 30 and an offset of 90, or shift of 90. Let's try to find the solution after 10 seconds, and let's start with a time step of 0.1. Only 100 delta t's between 0 and 10 seconds. As you can see, the pump pressure is very choppy. And if you remember from lecture 19, when we try to use this with a standard Runge-Kutta approximation, we got nothing. We actually got the solution to blow up, to go to infinity, as these error propagated. This instability induced by the valve actually caused instabilities that made the numerical error be large, and then propagate in time, and then give you meaningless solutions. All right, so we are going to let the resistance be 10, inductance be 0.1, the 2 capacitors be equal to 1, the resistance of the valve is 2, and the trigger pressure for the valve is 0. This system has 3 degrees of freedom, or 3 state variables, and the initial condition is 0, 0, 0 for pressure 1, pressure 2, and Q. This is the 2 sets of equations. So the 2 sets, there's a single set of equations with 2 sets of matrices and right-hand side vectors. Remember, in the 2 cases, you're solving for the same state variables, P1, P2, and Q. But then you have to switch between these 2 matrices and these 2 vectors, depending on whether the valve is open or closed. Okay, so this is the valve open coefficient matrix. This is the valve open right-hand side vector. This is a valve closed coefficient matrix. And this is a valve closed right-hand side vector. We're going to establish the tolerance at 10 to the minus 3. This is the epsilon. We're going to call it tol instead of epsilon. And it's just, we're going to apply it to the flow rate solution, to essentially the Q, which is state variable number 3. So we can apply it to whatever variable we want. We're going to actually apply it to all the variables. We can actually set up the system so that all variables, P1, P2, and Q, and all the variables in the state system of equations satisfy the same tolerance. For illustration purposes, I'm only going to do it for 1 state variable. So I'm going to try to keep the flow within the tolerance error of 10 to the minus 3. And see what happens. See if we can actually get an answer with that small of a number of time step, with a time step of 0.1, which we didn't get last time. So here's the code. Okay, it looks exactly the same. You initialize the solution vector using the initial conditions. So every column from k equal 1 to big K is each of the state variables, P1, P2, and Q. Well, each row, in this case row number 1, is the initial condition. All right, so we're going to loop over all time steps from 1 to n, n being the number of time steps, in this case 100, and calculate the current value of time, and we're going to calculate the current value of delta t, the step or the subdivided value of delta t, which we initially are going to set up as delta t. Okay, we're going to say our subdivided delta t is just the delta t that we picked, 0.1. We are going to ask the question, the conditional. If the valve is open, we're going to use A0 and B0. If the valve is closed, if the pressures across the valve is less than PV, means the valve is closed. So we're going to use AC and BC for A and B. All right. So we calculate K1. Then we ask the question again, whether the valve is open or closed, to be able to use A0, B0, or AC, BC. Calculate K2, calculate K3. And then after one time step, we check again whether the valve is open or closed. And then with that information, depending on what A and B are, we calculate K4. All right, so now we have K1, K2, K3, and K4. We add them together in this particular proportions and get Y1. Y1 is what we're going to call the first approximation, the approximation of Y using one time step, one full time step. Okay, notice that I haven't advanced in time. What I'm going to do next is I am going to break up the time step into two pieces, into two half steps. So the number of subdivisions is going to be 2. And I'm going to say each subdivision is 1/2 of the original time step. And I'm going to do exactly the same, but now notice that I have an inner loop that goes from 1 to 2. And in that inner loop, I'm going to calculate the solution 2 times. So I'm going to do half steps twice. Okay, so I ask the question whether the valve is open or closed, calculate K1, then I go half of that half time step and calculate and ask the question whether the valve is open or closed, calculate K2, calculate K3, then I ask the question after one half time step if the valve is open or closed, then calculate K4, then I am going to calculate Y2, which is the solution after one half time step, only 1/2 of that time step, and then it's going to do it again, because remember, this is inside of an inner loop that goes from 1 to 2. So I'm going to take 2 half time steps. So at the end of this inner loop, Y2 is going to contain the solution after one time step by having taken 2 half time steps. All right. Now I can calculate the error between the two. So I can calculate the error between Y2 and Y1. The third column of Y2, the Y2 is the third step of Y2 is after 2 half-time steps, and I can evaluate it. I can evaluate the error for all the state variables for P1, P2, and Q. All right, that's the error. So I can say that the solution, the next solution, according to the formula, is the solution Y1 plus this error. Okay. But then now let me find out if I need to go back in time and recalculate the solution, because it might not satisfy the tolerance. All right. And I'm going to say the tolerance is only going to be used for state variable number 3, okay, which is the flow. I originally said that I'm only going to try to satisfy the flow rate error, the flow rate tolerance. I don't care about the pressure. So you can do it for all the state variables, but I'm only going to do it for variable number 3. So I'm going to calculate the error again, okay, and then I'm going to say, well, is that error, if the error is less than the tolerance, is less than 10 to the minus 3, then the error is equal to the tolerance. Okay, so I don't need to do anything. However, the delta T max is going to be equal to delta T times the tolerance divided by the error to the power 1/5, according to the equation that we just wrote in the notes. If the delta T divided by the delta T max is larger than 2, so if this says that the maximum delta T that I found is actually smaller than the delta T that I use by at least a factor of 2, then I need to subdivide the domain, subdivide the time step in more than 2 subdivisions. Okay, so I calculate the new number of total subdivisions within that time step, which is the truncation of delta T over delta T max plus 1. Okay, so this is only calculated if indeed the delta T max was actually smaller than delta T, okay, by at least a factor of 2. So if that is the case, within this conditional, within this if statement, I am going to recalculate the solution, subdividing the time step into ns equal values, ns equal time steps. So this is adaptation, right? And within that conditional, or within that inner loop, I am going to go every delta TS, every small time step, which is equal to the delta T divided by the number of subdivision. And I am going to ask the question whether the valve is open or closed for K1, for K2 and K3, and then for K4, right? And then I'm going to recalculate the solution by looping within the inner loop and adding as many times as number of subdivisions that I have. Okay, so at the end of the day, if this condition was true, that condition was if NS, if the delta T over delta T max is larger than 2, so it's at least twice as much as the delta T that I needed to use, then the solution is going to be recomputed as the number of subdivided solutions, as the last subdivided solution. All right, so let's see if we can actually afford, with these modifications to the code, if we can actually get an answer using only 100 time steps or a delta T equal to 0.1, where last lecture we could not find an answer for. So as you can see, yes, even with that choppy type of representation of the solution, where the pump flow signal or the pump pressure signal is very choppy because the delta T is very, very large, very coarse, we actually find a solution. Remember that for these delta T, we actually found a solution to go to the power of 10 to the power of 243 or something like that, which is essentially infinity. So the solution diverges, again, giving us completely meaningless solution. Now the error is controlled, right? The delta T is being used. The original delta T is being used as long as we can afford it. But as soon as we don't satisfy that tolerance, then the delta T is reduced. So we maintain accuracy and also satisfy efficiency. So we are now able to implement this particular code in a feedback control loop. Same for the flows. See, now the flows are actually maintained. The flow that doesn't blow up to infinity. We find the Q is a red line, and this is the Q of the pump, which is calculated with a heaviside step function the same way, the same exact way as we did before. By the way, we did this for the first 10 seconds, so might as well show it for 10 seconds. I don't know why I was showing it only for 5 seconds, but this is it. This is a solution. And again, using this long version of the code that does the adaptive time stepping, and using this pressure signal, which obviously, as you can see, is very choppy. If we increase the size of the original the number of time steps, effectively decreasing the size of delta T, it's not going to affect. It's going to affect the efficiency of the solution, because the solution is technically going to be 10 times slower now that we broke up the time steps in factors of 10. But we're still going to satisfy the tolerance. And if a subdivision is needed, it's going to automatically be performed. And the answer is going to be just like this. All right, so let me leave it at 100 just to illustrate the fact that we are now able to get an answer with these coarse values of time steps, and then save these and post it on Canvas for you. So this is what I wanted to cover today, essentially solving the same problem while being able to afford more efficiency, because with adaptive time stepping, we don't need to actually use brute force to shrink the size of delta T to a very small value all the time. There are instances within the solution process where a large delta T is good enough, but there's instances where a lot of things are happening, like switching from one state to another, where you actually need to shrink the size of delta T, and this is what we effectively did. Not only that, we did it in a smart way by controlling the error, by ensuring that we're actually keeping within a tolerance that we pre-impose in the solution process. All right, so thank you very much for your attention, and I will see you next class.